by Nyquist stability criterion determine the stability of closed loop system. Okay, so we have to determine the stability of the closed loop system by Nyquist stability criterion, whose open loop transfer function is given by g of s h of s is equal to s plus 2 by s plus 1 into s minus 1. Comment on the stability of open loop and closed loop system. So let us consider the given open loop transfer function g of s h of s is equal to s plus 2 by s plus 1 into s minus 1. So from this open loop transfer function we can say that there is 1 0 lying on the s plane and 2 poles will lie on the s plane. So the 0 is minus 2 and the poles are minus 1 and plus 1. So if we observe the poles here, our poles are minus 1 and plus 1. So there is no pole which is lying on the origins. Okay, so in this open loop transfer function it does not have any pole at the origin on the s plane. Okay, so since there is no pole lying at the origin, so we must choose the Nyquist contour on s plane enclosing the entire right plane. Okay, so that is shown in the next slide. Okay, so we must choose the Nyquist contour on s plane that encloses the entire right plane. So that is this. So you can see this is our s plane, this is the right side of s plane. So this is our contour, so which is enclosing the entire right side. So if you observe in this contour, this contour has three sections. One is C1 section, this is the C1 section, and another one is C2 section, so this is the C2 section, and another one is the C3 section, this is the C3 section. Okay, so total 3 sections are there in this right side contour, which is called as Nyquist contour. So C1, C2 and C3, three sections are there in this Nyquist contour. Okay, so the mapping of each contour is done separately. Okay, after mapping each contour separately, we will combine all the separately mapped sections contours to get an overall Nyquist plot. Okay, so individually what are contours that we are going to get for each section, we will map them together. Okay, after mapping what are contour that we are going to get, so we will combine them to get the overall Nyquist plot. So let us start with mapping of C1, the section C1, mapping of section C1. So let us go to it. Okay, so mapping of section C1. If we observe here in this contour, in section C1, this omega, okay, omega, it is varying from 0 to where? From 0 to plus infinity. Okay, this is the part, C1 contour part, C1 section part. Okay, this is C1 section. So it is varying from omega equal to 0 to omega equal to plus infinity. Okay, so the mapping of this C1 is given by the sinusoidal open loop transfer function g of j omega and g of j omega h of j omega as omega is varying from 0 to plus infinity. Okay, omega is varying from 0 to plus infinity. Now we already have g of s h of s, which is s plus 2 by s plus 1 into s minus 1. Okay, so for this g of s h of s, we can convert this g of s h of s into sinusoidal open loop transfer function, and we can plot the polar plot for this. Okay, so whenever we want to determine the stability of the given system by Nyquist criteria, first of all we must have the knowledge of polar plot. So this is it. So s plus 2 by s plus 1 into s minus 1. So just I have rearranged the terms. Okay, so I want all these terms to be in the form of 1 plus some constant into s, or 1 plus s form. So I have rearranged the terms. I have taken 2 common in the numerator. So when I have taken 2 common in the numerator, I have got 2 into 1 plus 0.5s. In the denominator, here it is s plus 1, simply you can write 1 plus s. Here it is s minus 1, you can write minus 1 plus s. Okay, now replace s by j omega. Now replace s by j omega. If you replace s by j omega, you will get g of j omega into h of j omega equal to 2 into 1 plus 0.5 j omega by 1 plus j omega into minus 1 plus j omega. Okay, so we have converted the S domain terms into sinusoidal transfer function terms. So the open loop transfer function has been converted into sinusoidal transfer function. Okay, now if we have a sinusoidal transfer function, if you see here, this is the real part of this numerator term, this is the imaginary part. Similarly in the denominator, real part, imaginary part, real part, imaginary part. So you have 3 vector quantities, you can say, or complex terms. You have 3 complex terms, 1 in the numerator and 2 in the denominator. So you can determine the magnitude and phase angle for that. So 2 is constant. What is the magnitude here for this complex term in the numerator? That is root of 1 square plus 0.5 omega whole square, and at an angle of tan inverse of what? 0.5 omega by 1. Okay, whole divided by what is the magnitude of this rectangular form or complex term? That is root of 1 square plus omega square at an angle of tan inverse of omega by 1. Similarly for this term, okay, for this term, this is the magnitude, root of 1 square plus omega square at an angle of 180 minus tan inverse of omega. Okay, so once again I will explain. So this, for this numerator term, okay, magnitude is root of 1 plus 1 square plus 0.5 omega square, and angle is tan inverse of 0.5 omega by 1. So since it is divided by 1, no need to write 1. Similarly, next term, that is 1 plus j omega. For that, magnitude is root of 1 square plus omega square, and angle is tan inverse of omega by 1. Similarly, for this term, the magnitude is root of 1 square plus omega square, and angle is 180 minus tan inverse of omega. Now write down all the magnitude terms on one side and all the angular terms on the means aggregate all the magnitude terms and angular terms. Okay, so you will get 2 root of 1 plus 0.25 omega square by 1 plus omega square at an angle of minus 180 plus tan inverse of 0.5 omega. Okay, so this is the magnitude of g of j omega, h of j omega. This is the magnitude, and angle of g of j omega, h of j omega. This is our angle. Okay, so if we have the magnitude and angle, then for different omega values, okay, simply substitute, you assume some omega values. So here in this there is a omega term, there is a omega term here, and there is a omega term here. So you just assume some omega values and determine the magnitude value and phase angle value. Okay, so determine the magnitude and angle for this open loop transfer function. So this is my omega. So omega values I have assumed as 0, 0.4, 1, 2.0 and 10, and one term as infinity. Okay, so these are my omega values. Omega values are our wish, any value you can assume. Okay, so since omega is varying from 0 to infinity, I have made sure that 0 and infinity are included here. Remaining in between, your wish, any omega value you can assume. Okay, so for each omega value you just substitute that omega value in the magnitude formulae and angle formulae, and if you substitute omega equal to 0, you will get magnitude as 2 and angle as minus 180, and if you substitute omega equal to 0.4 in the above equations, magnitude equation and phase angle equations, you will get for 0.4 1.76 and angle is minus 168. If you substitute 1, then the magnitude of the open loop sinusoidal transfer function is 1.12 and angle is minus 153. If you substitute 2.0, magnitude is 0.57 and angle is minus 135. And if you substitute 10, magnitude is 0.1 and angle is minus 101. If you substitute infinity instead of omega, then you will get magnitude 0 and phase angle, angle is minus 90 degree. Okay, so based on this table, from this table, so what we can say that the locus of the sinusoidal transfer function g of j omega h of j omega, it will start from minus 180 degree axis at a magnitude of minus 2. Okay, isn't it? It will start at minus 180 degree axis at a magnitude of minus 2. Okay, when omega is what? 0, and it will meet the origin along 90 degree axis. This is it. When at 90, it will meet the origin at 90 degree axis when omega is infinity. Okay, so when omega is infinity, it will meet the origin at minus 90 degree axis. So based on whatever values that we have got, now we can map this C1 section of Nyquist counter. So for that, let us first of all, whatever our section C1 section is there on the counter, let us draw it as it is. So that's what I have done in the next slide. See, section C1 on S plane. This was our section C1. This section C1 where omega was varying from 0 to plus infinity. This is on the S plane. Now mapping of C1 on G of S H of S plane. Okay, mapping of this section C1 on G of S H of S plane. So just now as I have told you that the G of j omega H of j omega locus will start at minus 180 degree axis at a magnitude of minus 2. Okay, for omega equal to 0, for omega equal to 0 at a magnitude of minus 2. Okay, so the locus will start at minus 180 degree axis and meet the origin. This is our origin, isn't it? It will meet the origin along minus 90 degree axis when omega is plus infinity. Okay, so when omega equal to 0, magnitude was minus 2, and when omega is infinity, the magnitude is what? 0. Okay, so this is our counter. Okay, this is our C1 section counter on G of S H of S plane. Now let us see mapping of section C2. mapping of section C2. Okay, so the mapping of section C2 from S plane to G of S, H of S plane, it can be obtained by simply letting S is equal to limit r tends to infinity r e power j theta in G of S, H of S, and varying theta from plus pi by 2 to minus pi by 2. Okay, so now to map this section C2, okay, now to map section C2 from where? From S plane to which plane? G of S, H of S plane. Okay, what we have to do is we have to consider S is equal to limit r tends to infinity r e power j theta in G of S, H of S, and we must vary theta from plus pi by 2 to minus pi by 2, where S tends to r e power j theta and r tends to infinity. Okay, so here S is tending to r e power j theta and r is tending to infinity. Therefore, this 1 plus st term, okay, 1 plus st means, here if you see, here I have written G of S, H of S, this is 1 plus t into S, isn't it? It is in the form of this numerator. You just carefully observe the numerator and denominator terms. So here t is what? 0.5. Here t is 1. Okay, t value is 1, and here also t value is 1. Okay, so coefficient of S is nothing but t. Okay, so the term 1 plus st, it can be approximated as st, means 1 plus st is approximately equal to st. When is this condition applicable? When S tends to r e power j theta and r tends to infinity. Okay, so now based on this analysis, okay, so here G of S, H of S, what is it? 2 into 1 plus 0.5 S by 1 plus S into minus 1 plus S. So 1 plus 0.5 S means 1 plus st, it should be replaced by st. So 1 plus 0.5 S means it is simply 0.5 S. 1 plus S means S, minus 1 plus S means S. So 2 into 0.5 S by S into S, you just simplify it, you will get 1 by S. So G of S, H of S is equal to what? 1 by S. Okay, and what is S? S is equal to limit r tends to infinity, okay, r e power j theta. Okay, now let us substitute this S. Okay, let us substitute this S in G of S, H of S. Okay, so now, so this is G of S, H of S. Okay, at S is equal to what? Limit r tends to infinity r e power j theta. So let us substitute this S in this. What is G of S, H of S? It is 1 by S. So instead of 1 by S, you just write it down, limit r tends to infinity r e power j theta, that is, and now substitute this limit here, r tends to infinity. So instead of r, write infinity. 1 by infinity is nothing but 0. So 0 into e power minus j theta. Okay, so here it is. Here I must have written 1 by S, I didn't write it here. Okay, so I hope you have understood. So now when theta equal to pi by 2, what is G of S, H of S? Simply 0 e power minus j pi by 2, and when theta equal to minus pi by 2, G of S, H of S is equal to 0 e plus j pi by 2. Consider this as equation 1, consider this as equation 2. Okay, so from equation 1 and 2, what we can conclude is that the section C2 in S plane, it can be mapped as a circular arc of 0 radius around the origin, okay, on G of S, H of S plane, with an argument varying from minus pi by 2 to plus pi by 2. Okay, so here what did you get? G of S, H of S is equal to 0 e power j pi by 2. So and when theta equal to minus pi by 2, you have got g of s h of s 0 e plus j pi by 2. So our contour will lie at the origin. Okay, it will lie at the origin. Okay, so and the angle, the phase or the angle will vary from minus pi by 2 to plus pi by 2. Okay, our contour will lie at the origin. Okay, this section contour, C2 section contour will lie at the origin and it will vary from minus pi by 2 to plus pi by 2. Okay, so this C2 which is on the S plane, it is mapped as a circular arc of 0 radius. Okay, so since it is 0, okay, so its radius is 0 around the origin. Okay, in g of s h of s plane with which is varying from minus pi by 2 to plus pi by 2. So that is as shown in the next slide. This is our C2 section on S plane. Okay, this is the C2 section on S plane. So when you map it on the g of s h of s plane, so this is an arc, okay, which is varying from minus which is lying at the origin, whose radius is what? 0. R value is 0. Radius, R means radius here. So R value is 0, which is varying from minus pi by 2 to plus pi by 2. Okay, so here if I have not written, but here I can write minus pi by 2. Okay, here I can write plus pi by 2. Okay, you can write like that, but no, it is not required. So this is the C2 section which is mapped on g of s h of s plane. So this was our C2 section on S plane. This is the C2 section on g of s h of s plane. Okay, now let us go to the mapping section of C3. Mapping section of C3. So if you observe for mapping section of C3, if you go to our actual contour on S plane, this is our contour, isn't it? This was our contour. Okay, if you observe here carefully, for C3, okay, for C3 section, omega is varying from minus infinity to omega equal to 0. Omega is varying from minus infinity to 0. Okay, so the mapping section of C3, it can be obtained by the locus of g of j omega, h of j omega. Okay, as omega varies from minus infinity to 0. Okay, so if you compare C3 with C1, C1 locus is varying from omega equal to 0 to omega equal to plus infinity, where C3 varies from omega equal to minus infinity to 0. Okay, so they are exactly opposite to each other, isn't it? They are opposite to each other. Okay, so whatever polar plot that we have got for C1, okay, so exact mirror image of polar plot you will get for C3. So already we have got a polar plot for C1. So I will show you the plot for C1. So mapping section of C1, the polar plot that we have got is, this is the polar plot, isn't it? So for C3, since it is exactly opposite to C1, okay, so the inverse polar plot you will get, which is the mirror image of the C1 section polar plot. Okay, so there is no need to once again solve it, as we have done whatever we have done for C1. Same procedure you can follow, but no need to do that. Why? Because this is our C3. This is our C3. C3 is not there. This is our C3 section, which is varying from omega equal to minus infinity to 0. So exact opposite of C1 polar plot. Just now I have shown you the polar plot of C1. So this is just exact opposite of polar plot of C1. Okay, this is what you will get. So simply write down the mirror image. So here in theory also I have written inverse polar plot is given by the mirror image, okay, which is with respect to the real axis and real axis. Okay, so it was lying on the real axis there for C1. Here also the mirror image lying on the real axis you will get. Okay, so this is it. This is it. Now we had 3 sections, isn't it? We had 3 sections in the counter, Nyquist counter. There were 3 sections. C1 section, C1 section, C2 section, and C3 section. So for each section we have got the plot here, okay, on G of S H of S plane. So let us combine all these plots. Okay, so let us it is in technically we must say, let us map all these individual section plots. So if you map all these individual section plots, so what were the section plots that we have got earlier for M1, I'm sorry, for C1, not M1, for mapping of section C1, the plot that we have got was this. Okay, this is the plot that we have got for mapping C1. What about C2? This is the plot that we have got for C2. Okay, now for C3, mirror image of C1. C3 is nothing but mirror image of C1. This is it. Now let us combine all this. If you combine all this, this is the Nyquist plot on G of S H of S plane. Okay, so this, what is this? This is -2, isn't it? This is -2. This is -2. So if you see here, this is -2 means definitely from the origin there will be a -1. So this point is what? -1 plus j of 0. Okay, so if you observe the direction of this plot, it is in anti-clockwise direction. This plot is in anti-clockwise direction. So this is our Nyquist counter, and it is this plot is traveling in anti-clockwise direction, and it is encircling the -1 plus j0 in anti-clockwise direction only once. Okay, how many times it is encircling in anti-clockwise direction, this -1 plus j0? Only once. Okay, therefore we can say that the open loop transfer function has one pole at the right half of S plane. The open loop transfer function will have what? One pole, since it is encircling -1 plus j0 in anti-clockwise direction in only one time. Therefore we can say that the open loop transfer function will have one pole at the right half of S plane. Okay, so okay, so there will be one pole on right half of S plane. So open loop system is unstable, but closed loop system, okay, it will be stable. Okay, so the closed loop system will be stable, but this open loop system will be unstable, since one pole is lying on the right half of S plane. So that's what is I have written here. On traveling through Nyquist plot along the indicated direction, it is found that the point -1 plus j0 is encircled in anti-clockwise direction only once. So open loop transfer function has one pole at the right half of S plane. Since the number of anti-clockwise encirclements is equal to number of open loop poles on right half of S plane, closed loop system will be stable. So number of encirclements is 1 and number of poles on right side is 1. Therefore closed loop system is stable, but open loop system is unstable. Why? Because one pole is lying on the right half of S plane.